Alright guys, welcome back. So I told you we're starting intermolecular forces this week. You guys started off with a POGL, which hopefully introduced you sort of to the ideas of IMFs, and now I'm going to give you a little bit more detail. This correlates with section 12.6 in your textbook, so if you wanted to follow along that way, that's where you can find it. So first, a little general overview of inter versus intramolecular forces. So remember, in this class, we're going to be talking about intermolecular forces. Now, intermolecular forces is going to be the force that holds two molecules together. In this case, we're looking at two water molecules and the intermolecular force that's holding the two of them together. There are also intramolecular forces. That's what holds an actual molecule together within itself, or individual atoms within a molecule together. These forces are much stronger forces than intermolecular forces, but these are the ones that we're going to be focusing on in this class. Okay, so we're actually going to look at three types of intermolecular forces. Before we get into those three types, what's interesting to note is that the strength of the intermolecular force between the molecules or the atoms determines what state of matter the substance will be in. So it will determine whether it's a solid, a liquid, or a gas at room temperature. So depending on how strong that force is and what type of force it is will help to determine that. So stronger IMFs result in liquids and solids, and these are things that have high melting points and high boiling points. Whereas weak IMFs tend to result in gases. These have low melting points and low boiling points. So let's take a look at the relative strength of these bonds. And these are now listed from weakest to strongest. So the weakest one, and this is the one we'll start talking about first, is London dispersion forces. And then sort of the mid-range one is the dipole-dipole, and then the strongest one is the hydrogen bond. This video will focus strictly on London dispersion forces, and you'll watch the other videos, the dipole-dipole and the hydrogen bond videos, to get the rest of the notes. Okay, so London dispersion forces. This is what they call the default IMF. It's present in all molecules and all atoms. It doesn't matter if it's polar, it doesn't matter if it's nonpolar, it doesn't matter what the atoms that are making up that molecule. London dispersion forces will be there. Again, this is the weakest one. Now, what causes a London dispersion force to be present in all atoms and molecules? It really has to do with electron distribution, and something that we'll refer to here pretty soon as a temporary dipole. So because all molecules and all atoms have electrons, they all have London dispersion forces. And how unevenly distributed those electrons are will determine the type or how strong that London dispersion force really is. And the more uneven electrons that are present, uneven distribution of electrons that are present, the more London dispersion forces that are present. So let's take a look here. So I'm looking at two helium atoms here. So I have a helium atom here and a helium atom here. Now helium has two protons. It also has two corresponding electrons. Now, if I were to move these two helium atoms closer together, I'm going to see a couple things happening. So I move them closer together, and because I have electrons present here and I have electrons present here, the electrons that are present in this particular atom are going to be drawn to the protons that are found in this atom's nucleus, this helium atom's nucleus. So there will be attraction happening here. So these electrons are going to be drawn towards this nucleus. However, we're also going to be seeing repulsion because I have an electron here and an electron here. And we know that two things that have the same charge are going to repulse each other. So what's actually going to happen is these two electrons are going to want to move away. These two electrons are going to want to move closer to the proton, and these electrons, which we remember right here, are now going to be moving further away. So what we actually end up with are these temporary dipole moments where we end up with more electrons, so an overall negative charge over here, more protons from our more positively charged from our protons in our nucleus, more negatively charged because of the atoms that were over here, and more of a positive charge as our nucleus moves more to the side. So this creates what we call a temporary dipole. So even though there is really no dipole moment between these two helium atoms because they are the same, A temporary dipole is created because of these attractive and repulsive forces, and this is what gives you the London dispersion force. Okay. So the size of the dispersion force depends on how easily the electrons in the atom or molecule move, or we would call that how quickly they polarize, um, or how easily they polarize in response to a temporary dipole. So how easily they're able to create that dipole moment or create that temporary dipole will tell you the relative size of that particular dispersion force. And that will then tell you how large that electron cloud is that is going to be surrounding that nucleus is. So the larger the electron cloud is, the greater the dispersion force. And really the reason that this is because electrons that are further away from the nucleus are held together less tightly by the nucleus and can move much more easily, right? So ones that are further away can less of a tight bond to that nucleus, so they can move, they can polarize much more quickly and create these larger dispersion forces. Now, another important thing to note is that dispersion forces will increase with the molar mass. So if you look at the periodic table, and you look at the relative molar masses of individual elements, you should see this trend that as the molar mass increases, the boiling point should also increase. And so should the size of the dispersion force that you're looking at. So if I'm looking at, say, beryllium versus magnesium, beryllium has a relative molar mass of 9.01 and magnesium has a relative atomic mass of 24.31. By the standards of London dispersion forces, magnesium should have a stronger London dispersion force and should also have a higher boiling point as a result. So let's take a look at this. So I'm asking the question, which has a higher boiling point, Cl2 or I2? So based on what we just said on the previous slide, whichever one of these has the higher atomic mass should have the higher boiling point, and therefore should also have the stronger London dispersion force. So in this case, the relative atomic mass of Cl2 is 70.9 grams per mole, and the relative molar mass of I2 is 253.8. This is a much larger molar mass, so because I2 has the higher molar mass, it has the stronger dispersion forces and therefore also has a higher boiling point. Okay, this is where we're going to pause the video and you're going to do your first U-try. You will also submit this U-try on Canvas. So which has the higher boiling point, CH4 or C2H6? Go ahead and pause, and on the next slide I'll go over the answer here. Okay, here's the answers to number 1. So which has the higher boiling point, CH4 or C2H6? So the relative molar mass of CH4 is 16.05 grams per mole, and the relative molar mass of C2H6 is 30.08. So because this one has the higher molar mass, it should have the stronger dispersion force and therefore the higher boiling point. Okay guys, that's it for this one. To watch the next video, we'll learn about dipole-dipole moments. Let me know if you have questions. Thanks.